So, welcome friends to the lecture on the data purification in our course marketing research and analysis. So, since we have been discussing about data purification, so we will be continuing this also today, where today we will be covering with the last thing, that is the the last part of outliers and normality. So, in the last lecture we discussed basically about the type of outliers and how a researcher needs to be very careful in deciding whether to retain the outlier or to delete the outlier. Usually we think that if there is an outlier, the normal tendency is to remove it. No, not necessarily. You have to think logically, rationally, and then decide whether to maintain it or not to maintain it. Okay. So, continuing the same lecture, today we will talk about multivariate detection of outliers. In the first case we talked about the univariate detection, right, through the box plot and box plot, and then we talked about this bivariate detection, right, through a scatter plot, right. But we said there is a lot of problem in this bivariate detection because it gives rise to large number of combinations of pairs of graphs. So, the third way is the multivariate detection, which here we will use a new method, right. Because most multivariate analysis involve more than two variables, the bivariate method quickly becomes inadequate for reasons which we have discussed. First, they require a large number of graphs as discussed previously, when the number of variables reaches even moderate size. Second, they are limited to two dimensions at a time, yet when more than two variables are considered, the researcher needs a means to objectively measure the multidimensional position of each observation related to some common point. So, this is a limitation of the bivariate detection. So, this necessitates a requirement of the multivariate detection, which here we will use a Mahalanobis distance method, right. This issue is addressed by the Mahalanobis d square measure, right. So, Mahalanobis distance measure is the method which will be utilized to check the outliers. Now, a multivariate assessment of each observation across a set of variables. What it does basically is a multivariate assessment of each observation across a set of variables. Now, this is important. This method measures each observation's distance in a multidimensional space from the mean center of all observations, providing a single value for each observation no matter how many variables are considered. So, this is very important, that is why it is very important, because it takes a common point, and since it considers all the variables and still finds out a common point, it is more like it is more robust. This method is more robust. Higher d square values represents observations farther removed from the general distribution of observations. So, higher distances tell you that they are far away from the normal distribution, the general distribution of the observations. Drawback of only providing, what is the drawback? Every method has some drawback maybe. So, drawback of this method is that it provides no insight as to which particular variable might lead to a high d square value. Suppose there are 10 variables or 8 variables and you got a, let us say you have considered all of them. So, the advantage is that you have considered all of them, right, but the same thing also results in a disadvantage, because you cannot find out because of which variable does this outlier thing happen, right. So, that is the problem with Mahalanobis distance. So, how do you measure it? For interpretation purposes, the Mahalanobis d square measure has statistical properties that allow for significance testing, right. So, the d square distance measure divided by the number of variables, d square by df, this value is approximately distributed as a t value. Given the nature of the statistical test, it is suggested that conservative levels of significance at 0.005 or 0.01 be used as a threshold value for designation as an outlier. I will show you how to do that. Observations having a d square by degree of freedom is a number of variables minus 1, exceeding 2.5 in small samples and 3 to 4 in large samples are possible outliers. So, what is the rule of thumb? So, before going to this, let me show you how to measure the Mahalanobis distance. So, the Mahalanobis distance is measured through a simple regression method, right. So, go to regression linear, okay. It is immaterial what you take dependent and what you take independent in this case. For example, let me take in this case for example satisfaction, okay. I am taking satisfaction as my dependent variable, although because it looked more logical to me. Now independent I am taking all of these. Okay. Is there anything else I have left? Okay. Let us see. So I have taken all these variables. Okay. I need here something. So this is what I need, the Mahalanobis distance. Okay. So when I ask for the Mahalanobis distance, right. So what is happening? Let us see. Now you get a it has given you a model summary, right, a ANOVA which tells about the entire model, the residual statistics. So these are the values given, but our interest is not here, our interest is in the main file. Now let us go to the main file. Now in the main data set, if you see, a new variable has been created called the MAH_1. This MAH_1, right, is nothing but the Mahalanobis distance, as you can read it here, right. So this Mahalanobis distance is what we are interested in. Now the question is, how do I know from this value ki whether which one is an outlier or not? So now let us do one thing. So I create a new variable called through transform compute variable called MAH, let us say where is the keyboard here. Okay. So I am saying MAH, now I am giving 2, let us say the number I am giving is 2. So this is the second, right. So Mahalanobis distance 2 I am saying, I am giving it a name, right. So what I will do here is I will go to this place, right, I do not need it anymore. So what I will do is I will take this one, right, Mahalanobis distance, right, divided by the degree of freedom. Degree of freedom means, now how many variables had we taken? Now if you look back to the output, you can see now how many were there, 1, 2, 3, 4, 5, 6, 7, 8. Okay. So 8 minus 1, so 8 minus 1 divided by 7, that means, correct, and okay. So let us go to the folder again. Yes. Now you see a new value has been created, right. So this value is nothing but it is giving it is the d square by degree of freedom. Now as I had said, if you go back to the slide, d square by degree of freedom value exceeding 2.5 or in large samples 3 or 4. Now if you check at that, then let us see which are the two more than 2.5 at least. Now this is one, then is this is there is one 5.11 here, then there is 5.05 55 case, right. So okay. So we had got two cases, right. So we got two cases which had got a value of more than 2.5 or even 3. So which two were there? So case number 55 and case number 22 and 55, 5.11 and 5. So these two are basically our outliers. Now as a then once you have done with it, then you can decide whether to keep it or retain it or to delete it, right. So let us go to the final. So rule of thumb, univariate methods examine all the metric variables to identify unique or extreme observations. For small samples, that is 80 or few, outliers typically are defined as cases with standard scores of 2.5 or greater. I had told you the standardized score, if it is more than 2.5 then you will say it is a case of a outlier, right. For large sample sizes, increases the threshold value up to 4. Okay. So large samples are more than 80 or more than 100, right. Bivariate method focus on the use on specific variable relationships such as the independent versus dependent variables. It uses scatter plots with confidence intervals at a specified level, but I said this is more confusing and it is not relevant because you can just go through a multivariate method. This is the best method which is suited for examining a complete variate because it is taking all the variables together such as the independent variables in regression or the variables in the factor analysis, which we will come to later on. Threshold levels for the d square by df values should be in between 2.5 or 3 and 4. So this is basically how do you check an outlier, right. So now what from here, after the outlier part is covered, next we move to another problem that in data preparation, that is normality. What is this normality and why it is important? Normality means as whether the data is normal or not, as simple as that. Is it normal? Now what do you mean by normal? the data is normal when the data follows a normal bell curve, right, a normal Bell's curve. But suppose the data is like this, right. So, we say this is a positively skewed, skewed, right, positively skewed data. On the other hand, if you have something, for example, so we say this is a negatively skewed, because the tail is towards the negative, right, negatively skewed, right. So, whenever your data is skewed or it is kutotic, what does kutotic mean? Kutotic again means it is pickedness, right. So, instead of having a normal distribution, when it is picked, then also it is called a problematic data set, right. So, whenever our data sets are skewed or they are not normal, then the researcher has to, before getting into the final analysis, they have to first normalize the data. However, please remember that normality becomes less of significance when your sample size is extremely large. As your sample size goes on increasing, maybe in correspondence to the number of variables, it is very high, then in such cases your normality becomes lesser and lesser of a problem, okay, because the values try to normalize each other. The most fundamental assumption in multivariate analysis is normality, referring to the shape of the distribution, right. Okay. If the variation from the normal distribution is sufficiently large, all resulting statistical tests are invalid, because normality is required to use the f and the t statistics, right. So, if your data is not a normal data, your statistical analysis will give you all kinds of error results, right. Multivariate normality, which is a combination of two or more variables, means that individual variables are normal in a univariate sense and that their combinations are also normal, but there is a problem here. Now, what is it says? If a variable is multivariate normal, if it is multivariate normal, that means the combinations are also normal. It is also univariate normal, that means the individuals are also normal. But however, the reverse is not true, that means two or more univariate normal variables are not necessarily, the combination might not be normal, right. Individually they might be normal, but in the combination they might not be normal, right. So, you need to be careful here. The severity of normality is based on two dimensions, the shape of the offending distribution and the sample size. So, what is the shape and what is the sample size? As I said, with a very large sample size or an extremely large sample size, it gets corrected on its own. The researcher must not only judge the extent to which the variable's distribution is non-normal, but also the sample sizes involved. Impacts. How can we describe this distribution if it differs from the normal distribution? What will we say? How we will describe it? The shape of any distribution is dependent on two measures, kurtosis and skewness, which I had just shown you, right. Kurtosis means the pickedness, skewness is the tilting towards one side, left or right, okay. Kurtosis refers to the pickedness or the flatness of the distribution compared with the normal distribution. So, there are three types of kurtosis. Distributions that are taller, now this is one, this is taller or more picked than the normal distribution are termed as leptokurtic, right. Distribution that is flatter, this is the one, is termed as platykurtic, right. Mesokurtic distributions have a kurtosis of 0, that means 0 means normal, matching that of the normal distribution or the normal curve or also known as a bell curve. So, this is the normal general correct one, this is a problem, this is also a problem, right. So, these two are problematic situations. Kurtosis refers to the outliers of the distribution of data, it refers to the outliers. Data that have outliers will have large kurtosis, right. Data without outliers have low kurtosis, right. The kurtosis of the normal distribution is 0, there is no pickedness or flatness, right. The rule for evaluating whether or not your kurtosis is problematic is, if the absolute value of the kurtosis is less than 3 times the standard error 3 sigma x, then the kurtosis it is less than, that means k is less than 3 standard x sigma x, then it is not significantly different from that of the normal distribution, otherwise the distribution has kurtotic issues. So, we will see. Now, skewness refers to the height of the distribution whereas kurtosis refers to the height of the distribution, skewness is used to describe the balance of the distribution, that balance is tilted which side, to the right, to the left, which side. If it is unbalanced and shifted to one side, or is it centered and symmetrical with the shape on same shape on both sides. This is a positive skew, as I had told you, because the tail is trending towards the positive side. It is a negative skew because the tail is moving towards the negative side. Okay. Skewness means that the responses did not fall into a normal distribution, but were heavily weighted towards one end of the scale. Let us see an example. Income is an example of a commonly right skewed variable, is a right or a positive skewed variable. Income is a positive. Most people make between 3 and 10 lakhs per year in India, right, but there is a smaller group that makes between 10 and 50 lakhs, and even smaller group that makes 50 lakhs and above. So, the large section of the population is falling towards this side, right, and very less is falling towards the 50 lakhs and above, right. Addressing skewness may require transformations of data or removing influencer outliers. So, when you are talking about the skewness, in order to correct the skewness, either you need to remove the outliers, you have to remove it, or you have to transform the data and make it a normal data, right. So, we will see how to transform the data, right. What is the impact of sample size? Even though it is important to understand how the distribution departs from normality in terms of shape and whether these values are large enough to warrant attention, the researcher must also consider the effects of sample size. Sample size has the effect of increasing statistical power by reducing sampling error. In small samples of 50 or fewer observations, and especially if the sample size is less than 30 or so, which is the t-test requirement, significant departures from normality can have a substantial impact on the results. Suppose you have a small sample size and there is a non-normality of the data, of the distribution of the data, then it can have a very large bearing on the result, right. But if the sample size is 200 or more, this same effects may be negligible. So, with a higher sample size, it is it slowly goes reduces, the effect is reduced of the normality, non-normality. See, this depends on the kind of research you are involved in. Suppose in some researches the respondent number is itself a very small number, right, you do not get too many respondents, then in that case you need to be extremely careful about normality, right. But suppose you are doing a research on a very normal study which is where large number of respondents are available, then in that case maybe it is not a worrisome factor. So, statistical tests of normality. A simple Z test is a rule of thumb based on the skewness and kurtosis values. So, what it says is the most commonly used critical values are at a 0.01 significance level 2.58 plus minus 2.58, and for a 95% confidence level or 0.05 error level significance level it is plus minus 1.96. With this simple test, the researcher can easily assess the degree to which the skewness and pickedness of the distribution vary from the normal. Now, okay. So, how do you do it? First let us check whether there is a non-normality problem or not. Now, how do I go do that? So, go to in SPSS for example, go to analyze, go to not descriptives, go to analyze, go to explore. Can you see this? Now, what I am doing is I am taking all the variables, okay. Let us say I am showing you this 5, okay, only this 5, others I am not interested at the moment. So, what I am doing is I want to check, right. See, you can see even outliers from here also, correct. If you want to check the outliers, there is also a method in explore where you can see the outliers, okay. Plots. Now, I want a histogram because it gives me some kind of an idea, right. Okay. I want also a normality plot with tests. Why it is important I will tell you later on, but have a look at it at the moment, okay. I do not need this, okay. So, so now it is this value has come. Now, look at it. Now, how do I know whether there is a normality problem or not? Now, look at the skewness and kurtosis. Now, these two values, this statistic by standard error, statistic in this case for skewness is minus 0.085, by standard error is 0.241. So, if you divide these two, minus 0.085 by 2.241, this value should range between, suppose you are taking at a 5% significance level, between plus 1.96 to minus 1.96. So, just divide this at this you can divide 0.085 divided by 0.241, right. Similarly, for kurtosis also you need to do the same, right. So, all these values, skewness and kurtosis, if you can see these values, skewness and kurtosis values are given to you, just divide the statistic by the standard error and see whether the the value falls within this range of plus 1.96 to minus 1.96 for a 5% significance level, or for a 1% significance level plus 2.58 to minus 2.58, right. So, if it is suppose falling within this range of limit, then we say it might not be exactly normal, nothing it is not required to be perfectly normal, but at least it is within the desired level or value. So, you can proceed with the analysis. But however, if you have a value which is more than, let us say 2, or more than for a 5% confidence level study, 5% significance level, not confidence, 95% confidence. So, 5% significance level. So, if it is more than 2, then that means the data is skewed. Now, you can see some other values also, right. So, in this case minus 0.289 divided by 0.241. So, it is showing a negative distribution, but however, it is within the range of minus 1.96. Okay. So, the simplest way is let us go to the graph. So, the histogram this is you see, now it looks quite normal, right, although not a perfect normal, but it is normal. Okay. Right. So, is there anything that is not normal, which is not looking normal to you? Okay. Let us see some of them. Okay. Okay, this is also seems to be normal to me. Well, this is also normal. So, I do not think anything looks absurd out here. So, most of them are normal only. From a general visual inspection, you can say that they are mostly normal, but however, this the just that eye inspection might not be correct. So, what you can do is you can measure it through that method which I said and check whether there is a non-normal problem or not, right. What if there is a non-normality, that means the data is not normal. So, what do I do in this case? It is a very important question. How do I correct it? Price flexibility, just let us check it. One for I am having slight doubt with price flexibility. So, price flexibility is here 0.4, yeah, yes. Let us go to Salesforce image. Now, look at it, 0.493 divided by 0.241, my simple mathematics says if I multiply by 2, it becomes 482. So, this is even more than that. So, that means it is more than 2 times, right, of the standard error. So, there is a slight skewness. Let us go down and check the Salesforce image, right. So, Salesforce image. So, now this is from a normal observation, I thought it is not a very big problem, but it shows slight non-normality problem. So, when I have a non-normality problem, how do I address it is a $1 million question. So, what I can do is I can address this problem. So, let me show how to check that. So, in order to see if you have seen some normality, you can transform the data and a Salesforce image, right. So, what you can do is let us go back to the slide first. So, remedies for non-normality. So, first you observe whether there is a normality problem or not. Now, what is the remedy? Data transformation is the method that we use for making the data a non-normal data to a normal data. So, the methods are square root, logarithm, squared, cubed or inverse of the variable. So, these are some of the methods, but largely this method is followed to make a transform a data from a non-normal data to a normal data, right. So, how this logarithmic method is used, let me show you. So, compute variable, for this case we will write it compute variable, right, for Salesforce image, Salesforce, okay, I am just writing Salesforce, okay. Now, here I am going to delete this Okay. What I will do is I will take a arithmetic, I will go to a transformation. So, I am going for a logarithmic transformation, right. So, when I will go for a logarithmic transformation, I will go to the Salesforce image. Now, this Salesforce image will come to this place, correct. Now, I am doing automatically a log transformation, that means. Okay. So, now let us say OK. Now, let us go to the original file. Now, if you go to the original file, a new value has been created, a new column has been created called Salesforce, right. Salesforce, this column, now we are saying this should be normal, that means this is a representation of the Salesforce image only. So, it should be normal. Now, let us check whether it is normal or not. So, again I go back to explore and I reset and I take the final Salesforce and I go for a test. So, 0.354 by you see interestingly a very positive skewness has been now converted into a negative skewness, but that is very normal, nothing wrong in that. But however, the normality has been corrected. Now, you see 0.354, if I divide by 0.241, it should be less than in between minus 1.96 to plus 1.96. So, that means what? My normality problem has been corrected. Now, this is the data set that I am going to use now, right. So, once you have done with this data transformation and you have corrected the case, then you can proceed with your analysis and there is no issue at the moment, right. However, when you talk about normality, you need to understand two things, two concepts. One is called homoscedasticity and heteroscedasticity, right. Now, what is this homoscedasticity and heteroscedasticity? Now, it means what? If you can see it, it refers to the assumption that dependent variables exhibit equal levels of variance across the range of predictor variables, and this is desirable. Whenever the distribution of values, the variable is equal, when the data is scattered equally, if there is a variance is more or less equally distributed, then in that case it is a desirable case, which we say is called homoscedasticity, right. It is a tongue twister, please pardon me. And how do you check the homoscedasticity? Through a test called the Levin's test, right. Levin's test is a test of equality of variance, where generally what happens in any study, we say we tend to ignore the null hypothesis or try to reject the null hypothesis, but in the Levin's test we try to accept the null hypothesis. That means what? When we accept the null hypothesis, that means it should not get rejected, it should be accepted. That means what? We say that there is no difference between the mean and variance of one variable and another variable. That means what? If there is no difference, that means they are having a equal variance, right, and that is when, if they are having a equal variance, then only we can proceed with the study, right. So, these are cases where we want the null hypothesis to be accepted instead of rejected, right. Heteroscedasticity is a problem actually. Unequal variance, it generally gets corrected, but when the data gets normal, if your data is not normal, there is a large chance of getting this problem, but if as your data gets normal, heteroscedasticity problem is reduced. Let us see this case. This is a case of homoscedasticity. So, there is an equal variance, this is all distributed across the line, right, close to the line, but you see here the dispersion is too high, correct. You look at this point and look at this side, right, this it is as if like a funnel, it is going up, right. So, this is a case of heteroscedasticity, this is a case of homoscedasticity. So, how data normalization? Calculate the skewness and kurtosis, we have done that. Transform the data, usually log based transformation, so that also we have done. Finally, coming to the linearity. So, linearity is another problem. That means what it says, if first look at this, an implicit assumption of all multivariate techniques based on correlation measures of association, including multiple regression, logistic regression, factor analysis and structural equation modeling. So, the basic assumption is that data is linear in nature, right. Linearity refers to the consistent slope of change that represents the relationship between an independent and a dependent variable. Now, this slope, if it is not linear, it could be, if it is not linear, that means what? It is non-linear possibly. So, it can take the shape of a curve, and if it takes the shape of a curve, then the linearity is flouted, and in that case you have to be more careful about your final analysis, your statistical tests, right. If the relationship between the independent and the dependent variable is radically inconsistent, then it will throw off data analysis results. So, you need to be extremely careful with it. How do you test it? Deviation from linearity test, this test is available in the ANOVA test in SPSS, right. So, if you go to analyze compare means, put the composite independent variables, composite means the composite score of the independent variables and deposit and dependent variables in the list, then click on options and select test for linearity. To understand this, finally, if there is a linearity issues, you can still handle it by if you increase your sample size to a very large extent and you correct for normality, 99% of the time linearity gets corrected. If there is an issue of linearity and you have a large sample size with a normal data, then the case of linearity gets corrected on its own, right. However, if it is still non-linear, then the techniques used for doing a nonlinear study will be separately explained in the later on when I come to regression and such stuff, and there I will explain you, right. Okay, I think what we have done is for the day is very clear till now. What will you do if you have outliers, and what you will do if you have a problem of normality, and how will you handle it, right. Thank you very much.